All right, so let's take a look at section 4.3 about logarithmic functions. Now, up to now, every operation that you've ever seen has some kind of an inverse, something that undoes it. Addition and subtraction cancel each other out. Multiplication and division cancel each other out. Right? And squares and square roots, cubes and cube roots. Whenever you compose one of those functions with one of the other functions, you end up with just the original value. So if, for example, you have x plus 2, if you subtract 2, well, then you get back to just your x. If you have x times 3 and you divide by 3, again, you get back just your x. And if you have something like x to the 5th power and you take the 5th root, again, you end up back with x. Now, you'll note that this is from a previous section. This is what we're talking. This is what happens when you talk about inverse functions. All right? One of your functions does something, the other one undoes it and gets you back to where you started. So now we have a whole new type of function when we start talking about exponentials. So what is the inverse of an exponential function? That's what we're going to talk about here. So definition. So let x and b be positive real numbers. Where, this is going to sound familiar, it's going to sound like the restriction we had for exponential functions, where, let me say such that, your base is not equal to 1, y equals, and here this is read as log base b of x, is called an exponential function. Oh, sorry, it's called an exponential function. It's called a logarithmic function. Where, logarithmic function base b, that is important, which we'll see here in just a moment. A logarithmic function base b where the meaning of y equals log base b of x is interchangeable with b raised to the power of x, b raised to the power of y is equal to x. Just like that. Okay, so what does that mean? Well, first of all, notice that we make a distinction. It's a logarithmic function of base b. Why do we make that distinction? There's going to be different bases of a logarithm. Right? Okay, so what does the base do? Well, let's look at an example. Let's say I was asking for the log base 2 of 8. Just like that. So here the 2 is the base, the 8 is the argument. All right, so now this is asking you to perform a computation. It's saying take the log base 2 of 8. It's like saying take the square root of 8 or plug 8 into some function. Yeah? So here, whatever this is, it's going to give me an answer. So let me call that answer y, just so that it matches my definition. So here, that y is what I get when I take the log base 2 of the number 8. Well, what does that mean? Well, from our definition, what that means is, well, that's your base. That's your base. So here I have a base 2. So let me write down the number 2 as a base. Y, well, that's the exponent over here on this number 2. And here this 8, the argument, is on the other side of the equal sign. So if I say y is the log base 2 of 8, what that's saying, that should be an 8. Right? What I'm saying is that if I take the number 2 and I raise it to the power of y, I should get 8. So when we ask for the logarithm of a number, what we're asking for is what power should go on this base to get that answer? Well, right here, 2 to the power 3 is going to equal to 8. Just like that. But since 3 is the power that you would put on the number 2 to give you 8, that means that 3 must be the logarithm base 2 of 8. So right here, this would be the number 3. Let's see that again. Let's say I wanted to find log base 2 of, let's say, 32. Well, that's going to equal to some number. Now, here I put it as a y. Here I'm going to go ahead and put it as a blank. That way I can just fill in the blank here in a moment. So log base 2 of 32. Here I want to simplify. I want to find the log base 2 of 32. Well, again, by our definition, when we say we want the log base 2 of 32, we mean we want to start with the number 2, we want to raise it to some power, and that should give us 32. Okay, so what power do we put on the number 2 to get 32? Well, let's see. 2 times 2 is 4, times 2 more is 8, times 2 more is 16, times 2 more is 32. Oh, so I have to do that 5 times. So here, 2 to the 5th is equal to 32, which means that the log base 2 of 32 must be the number 5. All right? So that's what a logarithm is. A logarithm says what power should you put on this base? What power should you put on this base to give you that number? All right. Let's take a look at. Let's say we want log base. Let's say log base 3 of 9. Let's say we want to do log base 2 of 1. And let's say we want to look at log base, let's say log base 5 of 1 over 25. Okay. So pause the video for a minute and give these a try. Once you get to a place where you feel comfortable that you have the 3 answers, go ahead and unpause the video and we'll go over it together. All right, so here, log base 3 of 9 is equal to some number. That would be the number that you would have to raise the number 3 to give you the number 9. 3 to some power gives you 9. Oh, well, that's going to be the second power. 3 to the second power is 9. So log base 3 of 9 must be the number 2. Here, log base 2 of 1, that means that the number 2 is being raised to some power to give us the number 1. Well, that's got to be the power 0. After all, anything raised to the power 0 is equal to 1. So here, log base 2 of 1 must equal to 0. This one, we're saying, starting with the base of 5, we want to raise it to some power to give us 1 over 25. Well, I know 5 to the second power would be 25, but I don't want 25. I want 1 over 25. Oh, well, remember, to reciprocate a number, we use a negative power. So if 5 to the positive 2 is 25, 5 to the negative second power is 1 over 25. So here, log base 5 of 1 over 25, that must be the number negative 2. Now, this seems straightforward enough until you realize there's a bunch of numbers that you can't really do that with. For example, if we say, I want the log base 5 of 30. Well, okay, that means I'm going to take the number 5 and raise it to some power to give me the number 30. But I quickly realize that I don't know what that number is. Because 5 to the power 1 is 5. Okay, well, that's too small. 5 to the power 2 is 25. Well, that's still too small. But then 5 to the power 3 is, well, that's 125. That's too big. So 2 is too small and 3 is too big. Okay, so the answer is somewhere between 2 and 3. But I don't know exactly what that is. So here, log base 5 of 30, well, that's 2 point something. but I don't know exactly what it is. Well, that's okay, because we've experienced things like that before. For example, if I have the square root of 9, well, that's the number 3. If I have the square root of 64, well, okay, that's the number 8. But if I have, for example, the square root of 11, well, that's not a nice number, right? The square root of 11, that's somewhere between 3 and 4. 3 squared would be 9, 4 squared would be 16. But here I don't have an actual nice number that I can take as the square root of 11. But that's okay, because as we've seen in previous sections, whenever it can't be simplified, well, then that's our answer. The square root of 11 is a perfectly fine way of expressing a number. So here this cannot be simplified. We can estimate it. We can say, oh, that's 3 point something. And there are ways of finding out a really good approximation. So we can get really, really close. But again, you can't really get an actual decimal answer to this. It can't really be simplified any more than that. We're going to do the same thing for this. Here, okay, yeah, I know that the answer is somewhere between 2 and 3. 2 is a little too small. 3 is a little too big. So I could say my answer is 2 point something. But just like with the square root of 11, that's not really the answer. That's an approximation. So here, this, just like the square root of 11, we're going to say we can't really simplify it. Right? We can get an approximation. We could say this is more or less a certain number, but we're going to go ahead and leave this the same way we left the square root of 11. So in some of our answers, we'll get in some of our problems in later sections, we'll get answers like 5 and 12, and those are perfectly good answers. But we might also get answers like square root of 11 and log base 5 of 30, and those can't be simplified anymore. So those are perfectly good answers as well. We'll treat these as the simplest form of those numbers. So now let's see how this relates back to our exponential functions. Let's consider for a moment what happens when we take an exponential and a logarithm and put them together. And I say, well, what do you mean put them together? Well, that's a good question. You can put functions together by adding them, subtracting, multiplying, or dividing. But in this case, we're going to use a composition. So let's say we have a function f of x is equal to 2 to the power x. So we have an exponential function. And then let's say I have another function that's log, let's call that g, that's equal to log base 2 of x. Now let's say I compose these. So if I have f of g of x, well, that's going to be f of, well, I know g of x is log base 2 of x. Right? So that's f of my g. I've replaced that for g. But now f is the function that says whatever you plug into me, I'm going to use that as the exponent on the number 2. So that's going to be the number 2 raised to what we just plugged in, log base 2 of x. But look what this says. This says I have log base 2 of x. Okay, what I want to know is what power, so ignoring this base right here, what power should I put on the number 2 to get x? Okay, but now I'm taking 2 and raising it to that power. Let's say that again. If I have log base 2 of x, what I'm saying is, okay, if I have the answer to this, it'll tell me what power I should put on the number 2 to get x. Okay, whatever power, whatever number this is, if I raise 2 to that power, I'll get x. But now I'm going to take 2 and raise it to that power, which means I'm going to get x again. So notice, if I compose them, if I plug one function into the other, they cancel each other out. I'm left with just my x. Likewise, if I go the other way around, if I say g of f of x, well, that's going to be log base 2 of 2 to the x. Log base 2 of 2 to the x. I've taken my f, which is 2 to the power x, and I've plugged that into g, so log base 2 of 2 to the x. But again, look what this says. This says, all right, what power should I put on 2 to get 2 to the x? That almost sounds like a trick question, right? What power should I put on 2 to get 2 to the x? Well, I should put the x power on here. If I put the x power on here, I'll get 2 to the x. Okay, so that must be my answer, x. Oh, but again, if I take one of these functions and compose it with the other, they go away, and I'm left with just x. But by definition, that is what we mean by an inverse function. The composition cancels the two functions. Now here, it's important that these be in the same base, because if I do it the other way, if I do it with a different example, if I do it with a different set of bases, let's say I have f of x is equal to 2 to the x, and g of x is equal to log base 3 of x. Let me compose them, and here I'm only going to do one direction, because it'll be enough. If I say g of f of x, well, that's going to be g of 2 to the x power, which is which is log base 3 of 2 to the x power. After all, 2 to the x is the argument. G says whatever the argument is, we're going to take log base 3 of that argument. So that'll be log base 3 of 2 to the x. Now before, this was pretty much automatic. What power do I put on 2 to get 2 to the x? Well, obviously it's just x. 2 to the x is 2 to the x. But over here, I can say, what is the log base 3 of 2 to the x? Well, what power do I put on the number 3 to get 2x? I don't really know, right? It's definitely not x, because if I put an x on the number 3, 3 to the x will not be 2 to the x. If you think back to our previous section, those are two very different functions with different graphs. They're similar, but they're not the same. So here, these don't just cancel out. Now, that's not to say you can't do this. That's not to say this is nonsense. This is perfectly fine. You can plug this function in here, but they don't cancel out. So here, this does not just give us x. So when we say that these exponentials and these logarithms are inverses, it is important that these be in the same base. So if I have f of x is equal to 5 to the power x, and I say f inverse of x, if I want the inverse of this, it is a logarithm, but it has to have the same base as the exponential. Log base 5 of x. These are inverses. Likewise, if I start with a logarithmic function, I could say g of x is equal to log base, let's say log base 6 of x, and the inverse of a logarithm will be an exponential. But again, the bases must be the same. So if g of x is log base 6 of x, then g inverse of x must be 6 to the power x. There are a couple of special logarithmic bases. They're special because they get used very often. So here we have what's called the common log, and we also have what's called the natural log. The common log is usually written without a base. Now, if you write a base, that's not incorrect, but oftentimes the common log is just written as f of x equals log of x. All right, notice there's no base here. All right, the common log is base 10. So if you wanted to, you could write this as log base 10, and that would be absolutely correct. The other common base that we see very often is going to be the natural log. So this one would be something like f of x equals, the notation for the natural log is ln of x, like that. And the natural log is the log with a base of e. Now you remember e, we saw in a previous section, that was Euler's number, and that was a number that's approximately 2.7, more or less. There are some special properties of the natural logarithm which make it useful over other logarithms, but for now we're just going to treat this as another logarithm that happens to have a specific base. Right? So here, this is log base e of x. That's what this one means, the natural log. All right? Because they have these specific bases, keep in mind that since logarithmic and exponential functions are only inverse to each other if they have the same base, and if they don't, well then they're not. Here, the inverse function of the common log would be 10 to the power x, whereas the natural log would have the inverse e to the x. So if you have f of x is equal to the common log, then f inverse is 10 to the power x. Or if your original function was 10 to the power x, the inverse would be the common log. If you have a function that's defined by the natural log of x, then the inverse function is given by e to the power of x. Or if your original function was e to the power of x, the inverse would be the natural logarithm of x. So let's take a look at some graphs now. In some previous sections, we saw that a function and its inverse have a relationship when you look at their graphs. In particular, if you look at the graph of a function and you look at the graph of its inverse, they're a mirror image of each other across the line x equals to y, across the diagonal line that crosses through the origin that has a slope of 1. Well, we just said that the exponential functions and the logarithmic functions are inverses. And since we worked very hard to find the graphs of the exponential functions in a previous section, we can now use that information to help us very simply find the logarithms graphs. So consider the exponential growth function. Consider f of x to be a to the x. Now here we want to look at just exponential growth, so we're going to look at this only when the base is greater than 1. We'll look at the exponential decay model separately. Just like that. Okay, so if f of x is equal to a to the x for a is greater than 1, that's the exponential growth function. All right, well, we know what that's going to look like. It's going to cross through the point 0, 1. After all, anything to the power 0 is 1. So 0, 1. It's going to have the x-axis as an asymptote. And here I'll do this in pencil. So here I have a horizontal asymptote. And now my graph, this is the exponential growth function. So it will grow to the right, and so that means it'll decay down, it'll shrink down toward the asymptote on the left. All right, so that's our exponential growth function. All right, well now we know that the inverse of the exponential function would be the logarithmic function. Now remember, we have to keep the same a here. We have to keep the same base. So f inverse of x would be the log base a of x. Now keep in mind, these are the same base, which means it's still greater than 1. All right? This a is the same as that a. Well now, because these are inverse functions of each other, the graphs are simply a reflection across this line x equals to y. All right, well let's do that. Here, 0, 1, if you reflect the x and the y, instead of 0, 1, now you have 1, 0. And now, the asymptote, which was y equals to 0, if we're going to reflect everything, instead of y equals to 0, now we have an asymptote x equals to 0. Or in other words, instead of having a horizontal asymptote, the exponential function has a horizontal asymptote. Now our logarithmic function will have a vertical asymptote. So exponentials have a horizontal asymptote, whereas logarithmic functions, and here I'm going to go ahead and abbreviate that as logs because logarithmic is just such a long word to say and a long word to write. Logs have a vertical asymptote. So my graph will follow this line. Now notice here, as my x becomes negative, my y value is still positive, but it gets very, very small. Well, now say the same statement, but flip x and y. As y becomes negative, x is still positive, but it's going to get really, really small. It's going to follow the asymptote. So this part right here reflects down to this part over here. Here, as x gets larger, y gets larger. That's going to curve along up toward the y-axis. So here, we're going to do the same thing. As x gets larger, y gets larger. Okay, now reflect the statement. As y gets larger, x gets larger. Okay, and this is going to bend up toward the, well, not the y-axis anymore. It's going to bend toward the x-axis. And it looks like this. Notice that we knew a bunch of things about the exponential function. We knew its domain, we knew its range, we knew its intercept, we knew its asymptote. Well, we worked very hard to find all of those things, but now, because this is simply a reflection of this, we can now assume all of those things to be true for our exponential function, for our logarithmic function. So our logarithmic function has a domain. Well, look, starts at 0 and just goes to the right. It doesn't touch 0, that's an asymptote. Okay, so it's from 0 to infinity and doesn't include the endpoints. On the other hand, the range, well, that does go down forever and it does go up forever. So that's going to go minus infinity to infinity. Notice that's the domain and range of the exponential function, but flipped around. Right? The domain of the exponential function was negative infinity to infinity, and that's the range now. The range of the exponential function was from 0 to infinity, and that's the domain now. Everything gets flipped. Notice 0, 1 was a y-intercept. Well, now 1, 0 is an x-intercept. 1, 0 is the x-intercept. And I have an asymptote. It's no longer horizontal. It's now been flipped vertical. So we have the y-axis is a vertical asymptote. So whereas in a previous section we took a bit of time to map all of these points, we graphed a bunch of things and found all the relationships and found all of these one at a time, here we reflect and it's all automatically there. While we're at it, let's go and write down some of the properties that we saw in the last few examples. We've seen a few things here. In particular, if you, oh, where did that go? Here. If you take a log base 2 of 1, that's going to give you 0. Well, you know, that could have been any base. I could have said log base 20, because 20 to the 0 is also 1. Right? It doesn't matter what that is. So let's list a few other basic properties of logarithms. The one we just saw is, so let's see here, other basic properties. If I have log base anything of the number 1, that's going to give me 0, as we saw just a second ago. Now, if you want log base b of b, well, again, the way logarithms work, what power should I put on b to get b? Well, that's the power 1. b to the first power is b. So log base b of b is equal to 1. And then the other two properties are the ones that we saw when we define our logarithm as being the inverse of our exponential. They are these properties here. Namely, if you compose an exponential with a logarithm, or if you compose a logarithm with an exponential, either way, you get back what you started with. So here, if you take log base b of b to the x, what power do you put on b to get b to the x? Well, it's almost like a trick question. You put x on there. b to the power x is b to the power x. And if you flip that around, if you compose in the opposite direction, b to the log base b of x, again, will just give us x. So these are some basic properties that we've seen scattered out, and here let's just list them together. That way they're all together in one nice package. Now, of course, that's only half the story, because here we're looking at the exponential function, and its inverse is the logarithmic function. Well, yeah, but here we were restricting ourselves to a greater than 1. But we know a doesn't have to be greater than 1. It can also be between 0 and 1. That was the exponential decay function. So let's go and consider that. Consider f of x to equal to a to the x, so same kind of problem, but now for a to be less than 1. Now remember, when we say less than 1, exponential functions should have a positive base. So when we say greater than 1, we still mean, when we say less than 1, we still mean greater than 0. So this should be positive. So somewhere between 0 and 1. All right, well, if that's a number that's less than 1, then this must be the exponential decay graph. And we know what that looks like. that's going to have a point here, 0, 1. That's going to have the x-axis as a horizontal asymptote, and it's going to decay. It's going to start off big and shrink down toward the asymptote. It's just this one, but flipped around. All right. So now, if that is my exponential with a base less than 1, to find the inverse of that, to find the logarithm with a base, to find the logarithm with a base less than 1, we're going to go ahead and reflect that across this line. Once again, x equals to y. So if x is equal to y, here that's a point that touches the line x equals to y, so we're going to go ahead and leave that one there. But now everything else gets reflected. Here 0, 1 becomes 1, 0. Just like it did before, 1, 0. Before we had a horizontal asymptote for our exponential. Well, now y equals to 0. If we flip x and y, that is now x is equal to 0. So just like before, we're going to have a vertical asymptote for our logarithm. And so now our graph will simply be this exponential decay model, but reflected. So it's got to cross through here. It's got to cross through here. It's got to follow our asymptote. And then over here, this now is reflected on this way. Notice this part in blue is now reflected in this part in red, follows this asymptote versus following that asymptote. And this part in blue is now reflected as this part in red. Notice that it does have all of our same properties as before. The domain is still from 0 to infinity. The range is from negative infinity to positive infinity. 1, 0 is an x-intercept, and the y-axis is a vertical asymptote. All of these properties are true for both the exponential, so for both the logarithmic functions with a base that's greater than 1, or for one that has a base that's less than 1. Whenever you have a base that is greater than 1 for an exponential function, this is called an exponential growth function. Here, we're going to share the same name, except now instead of exponential, this is logarithmic. Okay, fine. That makes this the logarithmic decay function. Or rather, a logarithmic decay function. There's going to be others depending on what your base is. Oh, my apologies. This should be logarithmic growth, because after all, a is greater than 1. This will be logarithmic decay. A is less than 1. Our exponential function decays, and so does our logarithmic function. Right. So, just like before, we have a new set of parent functions. Let's go ahead and draw out what we have. If you remove all of the details and only leave some of the most general properties of your logarithmic functions, you pretty much have every logarithmic function you could ever have as one of these basic two. You have logarithmic growth. Here, this is what happens if you have f of x equals log base a of x for a greater than 1. Notice that passes through 1, 0. It has the y-axis as an asymptote. And over here, if I have f of x equals log base a of x, notice that's the same function. The difference is now I have a base that's less than 1. Note, bases for logarithmic functions, just like bases of exponential functions, should be greater than 0. So here I'll even write it that way, between 0 and 1. If that's the case, then we still have the same point. 1, 0 is still our x-intercept. We still have a vertical asymptote there, but now our function will decay instead of grow. Just like that. And if you notice, these are just reflections of each other. This starts here, down, and then out. Here, this starts down here, up, and then out. They're reflections. If you flip this one upside down, you get this one. So now let's take these and look at some transformations to graph some other logarithmic functions. So here, for example, we're going to go ahead and sketch the graph of f of x is equal to, let's say, log base 3 of x minus 1 minus 2. So we're going to begin with a parent function. Remember, the parent function is the most basic function without any additions, subtractions, or multiplications. So our parent function, f of x, equals log base 3 of x. Well, that's a logarithmic function. And since the base is 3, which is bigger than 1, that'll be my parent function. So let's start off with that graph. This will have my exponential, this will have my logarithmic growth curve. So this will pass through 1, 0. It's going to start down here and go up and out toward the right. It'll follow the y-axis as an asymptote. Like that. Okay? So now, anything that's different between the parent function, and I should call it p of x, or parent, everything that's different between my parent function and my final function must result in some kind of transformation. Well, I see two differences. I see a minus 1 here, and I see a minus 2 here. Remember, whenever you add or subtract inside the argument, whenever you add or subtract to the x value, that's going to move things left or right. But if you add or subtract on the outside of the function, if you add or subtract after the whole thing has been put together, that's going to translate things up and down. So here, this minus 1, that's going to cause everything to move to the right by 1 step. And this minus 2 will cause everything to move down by 2 steps. So let's go and do that one step at a time. We're going to go ahead and move everything over to the right. I'm going to do this in pencil still because it's not my final answer. If I take this graph and I move everything over to the right, notice this point, instead of being 1, 0, that is now 2, 0. But also, remember that my vertical asymptote was the y-axis. If everything moves over 1 step, that includes where the asymptote is. So now instead of having the y-axis as an asymptote, now I have this line as an asymptote. Now I have the line x equals to 1 as an asymptote. Okay. Well, now, my graph should still look the same. It's going to follow the asymptote and go through the point up and to the right. The only difference is now it's shifted over to the right. Well, now the next thing I want to do, I want to move everything down 2 steps. Now, if this is the vertical line, and I shift it down 2 steps, it's still in the same spot. It's still the same vertical line. So that doesn't change my asymptote at all. My asymptote will still remain in the same place. It'll still remain x equals to 1. But now, this point will go down 2 steps, 1, 2. And now instead of being 2, 0, this would be 2, negative 2. Now it still has this shape. It's going to go down toward the asymptote on the left and up and out toward the right. And there's my graph. Here's my f of x. Okay. Let's take a look at another one, just like that. Let's consider the following function. Let's graph. Let's use f of x equals 2 minus the natural log of x. Oh, let's do natural log of x plus 1. Okay. Now remember, the natural log of x is not some unusual new function. Rather, it's just a function, a logarithmic function with a base of e. So here, recall, that just means a logarithm base e. And since e is greater than 1, e is about 2.7, give or take, then that means that this will still be exponential growth. All right, so let's go and start off with that. Our parent function is the natural log of x. And since that base is greater than 1, that means that your function, that means your exponential function will have a growing pattern. It'll be logarithmic growth. So let's see here. We have a parent function that looks something like this. It has this asymptote. It's going to cross through the point 1, 0. It's going to go down toward the asymptote and up, out, away from the asymptote. And that's just our parent function. That's our p of x. So now once we have this, every difference between here and here must be caused by some transformation. Now this one is a little bit misleading. It might help if we rewrite this just ever so slightly differently. I'm going to write this as negative natural log of x plus 1 plus 2. Now this says exactly the same thing. I have negative natural log of x plus 1, and all I've done is I've moved that 2, which is a positive, over to the back. All I've done is I've rearranged some terms. But now, what might have looked like there was only 1, 2 different actions, it turns out that there's 3 different transformations. And remember what these transformations do. If you have plus or minus inside of your function, inside of your argument, that's going to move things left and right. Negatives cause a reflection, and adding or subtracting on the outside of the function move things up and down. So here, this is going to cause everything to move to the left by 1. Because this negative is on the outside, it's going to cause everything to flip upside down. So this one is upside down. And that plus 2, as it's on the outside of my function, is going to move everything up by 2. All right, so let's go ahead and cause our transformations. There's 3 of them. Parentheses go first, so we do this transformation first. Multiplication and division goes second. So notice here you have, that's like saying times negative 1. And then finally your addition, subtraction. You're following the order of operations. Parentheses, exponents, multiplication, division, addition, subtraction. So left by 1, that's in the parentheses, that goes first. Okay, so if that's my asymptote, if I move everything to the left by 1, well, now I have a new asymptote. This point goes from 1, 0. I move it to the left by 1, and now it's at the point 0, 0. It's at the origin. I still have the same graph, the same size, the same shape. It's just now moved over a bit to the left. Okay. All right, so now the next thing I want to do, upside down. This is a vertical asymptote. If I take this and flip it upside down, it's still the same vertical asymptote. A vertical line flipped upside down doesn't change its location. So I still have the same asymptote, but what does change is all the stuff that was, and here, you know, I'm going to go ahead and label this as transformation number 1. That way we keep track of them a little bit better. Transformation number 2 is making things go upside down. So this part that was down here has now been flipped up here. And this part that was up and out this way, we're now going to go ahead and reflect it over this way. Something like that. All right. And that's my number 2. And finally, I'm going to go ahead and move this up 2 steps, and that's going to go into my writing, but oh well. I'm going to move everything up 2 steps, and that'll be my 3rd transformation. So that's going to move this point up 2 steps, 1, 2. The vertical asymptote, if I take a vertical line and move it up, it's still the same vertical line in the same position. So that vertical asymptote has not changed. It is still x equals to negative 2. Oh, sorry, that should be x equals to negative 1 because I moved the left by 1. And now I'm going to draw this same graph, but now I'm going to draw everything moved up by 2 steps. So now this will be up here, a little bit higher. This won't go down quite as low. And here's my graph. So this is my final result, and that's my f of x. Just like that. Note that we can find our domain and our range just by looking at our graph. Here, the domain of this function is everything to the right of negative 1. So from negative 1 to infinity. Negative 1 is a vertical asymptote, so you don't even get to negative 1. So we're going to use round parentheses on both. If we go back to one of our previous examples, here, the domain is everything to the right of positive 1. Okay, so right here, that's going to be the domain is everything from positive 1 to infinity. From here, out that way. Okay. We can actually find the domain of the logarithmic function without having to graph it. Because if you look back at our logarithmic functions, it doesn't matter if we have logarithmic growth or logarithmic decay. The graphs of these show us that the parent functions have a domain that goes from 0 to infinity, from 0 to the right, from 0 to the right. What that means is that the x values of a logarithmic function must be greater than 0. Well, yeah, but then if I have some function, that means the argument, the stuff that gets plugged into the logarithm, must be greater than 0. So for example, let's say I want to find the domain of this. F of x is equal to, and let's just go ahead and grab one from our homework. Let's say log base 2 of 2x plus 4. Something like that. We know that whatever goes in here must be positive. Okay, so the domain is just whatever makes sure that this stays positive. Since the argument of the logarithm, and it doesn't matter what the base is, since the argument of the logarithm must be positive, well, then that means we want to take the stuff that's in the argument and we want to find what makes it positive. Well, another way to say positive is to say it's greater than 0. So what we're really looking for is we're looking to make this greater than 0. Not greater than or equal to. The argument can't be 0. It has to be greater than 0. Okay, so that's simple enough to solve. We just subtract 4 from both sides. So that'll give me 2x is greater than negative 4. And now I divide both sides by 2, and that'll give me x is greater than negative 4 over 2. But now, since I've isolated my x, that means I have my domain. Here I can simplify this. Negative 4 over 2, that's just the same as saying negative 2. But now the domain of my function is all the x's that are greater than negative 2. My domain is going to be all the x's that are greater than negative 2. So from negative 2 on to the right forever. From negative 2 to the right. We don't include negative 2. This is strictly greater than. So our domain is just from negative 2 to infinity. To find the domain of a logarithm without having to worry about graphing it, you simply take the argument and find what makes it greater than 0. This will come in handy in later sections when we start looking at equations that involve logarithms. Logarithmic equations can be solved, but much like solving equations back in chapter 1, we do sometimes have extraneous solutions. We do sometimes have solutions that look like they work based off of what the algebra looks like, but if you have something that is not in the domain, even if it looks like it should work, it can't work because the function's undefined for those values. So in later sections, when we start looking at solving equations that involve logarithms, if we want to figure out what values need to be excluded, obviously graphing it would work, but it's probably far simpler to just look at the domain of the function without having to go through and make a graph. So for our last example, same kind of problem. Let's go ahead and find the domain. We don't need the full graph, just find the domain of, let's take the function f of x to equal to, let's use the common log. So log base 10, right? The common log of x squared minus x minus 12. Now here, the fact that we're using the common log doesn't change anything about how this works. The domain of every logarithm should be what values make your argument positive. Not zero, not negative, but strictly positive. The fact that this is the common log doesn't make it any different from the previous example where we were looking at log base 2. If we had natural log base 2/3, log base a fifth, none of that would matter. So here, you should pause the video and give this a try. See if you can find the domain of our function, and when you get to a part where you feel like you're comfortable, come back and we'll go through it together. All right, so let's take a look here. If you take the log of x squared minus x minus 12, we want to find whatever makes this argument positive. Okay, so that's going to be whatever makes that argument greater than 0. Not greater than or equal to, but strictly greater than. Well, this is a kind of problem that we saw in the previous chapter when we were solving polynomial inequalities. Thinking back to what we did in chapter 3 to solve polynomial inequalities, what we did was we first set one side equal to 0. We already have that. The next thing we did was we found the zeros of this polynomial. There's a couple of ways we can do that. One way is we could use the quadratic formula. A is 1, B is negative 1, C is negative 12. But this one is simple enough to factor. After all, what two numbers multiply to give you 12 and add up to give you negative 1? Well, negative 4 times 3 is negative 12. Meanwhile, negative 4 plus 3 is negative 1. So that factors as x minus 4 and x plus 3. Oh, but if x minus 4 is one of my factors, then positive 4 must be one of my zeros. So my zeros are positive 4. And here, if x plus 3 is equal to 0, then my other 0 must be negative 3. So now once you have your zeros, you're going to take those and you're going to place them on the number line. All right. Negative 3 is the lesser of these, so we'll put negative 3 on the left. 4 is the greater of these, so we'll put that one on the right. And now we need some numbers that fall in each of these three intervals to test whether or not that interval is part of my solution, whether or not that interval is part of my solution. Same thing for that interval. So we need some number that falls in each of these intervals. Well, some number between negative infinity and negative 3, I will use negative 4. Some number between negative 3 and 4, go ahead and use 0. And some number between 4 and infinity, I'll go ahead and pick 5. So now I can take each of these and substitute them one at a time into my inequality and see which ones work. Maybe one of them works, maybe two of them work, maybe all three of them work. So let's take a look. Let's set x equal to negative 4. We'll use this first test point. If that happens, well then we're going to get negative 4 quantity squared minus a negative 4 minus 12 is greater than 0. And we want to see if that's true. Negative 4 squared is positive 16. Double negative makes that a plus 4 minus 12. is greater than 0. 16 plus 4 is 20. 20 minus 12 is going to give us 8. And now 8 is greater than 0. Well, yeah, that's true. So because that's true, that means that this number is a solution. And so that means all of the numbers in this region are a solution. Okay, let's try 0. If x is equal to 0, that means 0 to the second power minus 0 minus 12 is greater than 0. Well, 0 minus 0, all that's gone. That's just 0. So really, the only thing we have here is that negative 12. Negative 12 is greater than 0, and that's false. Negative numbers are not greater than 0. So because that's false, 0 is not part of my solutions, and so that means none of these numbers between negative 3 and 4 will be part of our solutions. Finally, the last thing, we're going to try positive 5. Maybe it'll work, maybe it won't. Let's see 5 here. If we plug in 5, that'll be 5 squared minus 5 minus 12 is greater than 0. 5 squared is 25 minus 5 minus 12 is greater than 0. 25 minus 5 is 20 minus 12 is greater than 0. And yeah, that's absolutely true, because 20 minus 12 will give us just the number 8, which is in fact greater than 0. It's a positive number. So that's true, which means that 5 is a valid solution, and so all of those numbers are valid solutions. So here, the domain of this function, the domain of f, the common log of x squared minus x minus 12, is all the stuff between minus infinity and minus 3. Now remember, this is an exclusive inequality, so we don't include any of our boundaries. And all the stuff between 4 and infinity, don't include any of your boundaries. And here we take the union of those as they are, two separate parts to a single answer. Just like that. Graphing this one, incidentally, would be a lot more complicated because we haven't seen transformations like this. We don't know what those look like exactly, but we don't need to know what the graph of this looks like because we can find its domain without the graph, and the domain is what we'll primarily be interested in when we start solving equations with logarithms in the coming sections. So that's it for the section. I hope you all have a nice day.